So in this video we will talk about the eigenvalues and the eigenvectors. So if you have a square matrix whose size is n by n and you have a scalar, that scalar lambda, where lambda is a real number, this means lambda belongs to real number. So if you have a matrix, a square matrix of order n and a real number, and you have a non-zero vector which is n tuple, Rn means the vector x is n tuple, so it has n different entries. So the equation Ax is equal to lambda x is called the homogeneous equation, and in this equation lambda is called the eigenvalue and the vector x is called the eigenvector of A. So it's very simple. If you have this kind of equation, in this equation A is n by n matrix, x is an n tuple. N tuple means it has n entries. In other words, it is a column vector whose values are n. And lambda is a scalar, it is a real number. Then lambda is called the eigenvalue of A and x is called the eigenvector of A. Next we have a characteristic equation. The characteristic equation can be found by using the determinant of A minus lambda I n is equal to 0. How we have found this equation? Initially, you have this equation which is Ax is equal to lambda x. If you rewrite this equation in this way, Ax minus lambda x is 0. Then if you take x common from both of the values, then A minus lambda times identity matrix times x is 0. So you will get this equation. You can check that this is A minus lambda I, this value. So this equation has a unique solution if and only if this matrix has an inverse, and this matrix can only have inverse if its determinant is not 0. But here we have supposed that this determinant is 0. So that means we are not interested in the solution. So whenever you have this kind of equation, so its corresponding characteristic equation is determinant of A minus lambda times identity matrix and equate is it equal to 0. Then this equation is called the characteristic equation. The good thing of this characteristic equation is that the solutions of these equations are the eigenvalues of A. So if you want to find the eigenvalues of A, then you have to solve the characteristic equations. So here is an algorithm in which you have to find the eigenvalues and the eigenvectors of A. So here are the steps. So first of all, you have to determine the determinant of A minus lambda I n, which is exactly this thing. So secondly, since you are going to find the eigenvalues, so I told you equate this determinant equal to 0, then you will find the eigenvalues. So the next step is solve the characteristic equation for lambda, so which are the eigenvalues of A. So once we have found the eigenvalues of A, then for each eigenvalue lambda I means, for example, if there are 2 or 3 eigenvalues, I will assume the first value is lambda 1, the second value is lambda 2, the third value is lambda 3, up to so on. So that's why I have written lambda I. That means as many eigenvalues which are found from the previous algorithm. So for each eigenvalue lambda I, we will solve the characteristic an equation. The equation is A times A minus lambda I times X. So for each lambda I, we will solve this equation. So here you have lambda I. So for each value of lambda I, you will put this value here. Then we have to find the null space of this equation and the basis vectors of that null space. So I will tell you how to find the basis vectors of this null space. So this is the algorithm. When we will do an example, this last thing will be clear. Now there are some key properties. So the first property is the sum of all the eigenvalues is always the trace of the matrix. And the product of all the eigenvalues is equal to the determinant of the matrix. And the third key point is eigenvector for different eigenvalues are linearly independent. So now we will solve an exercise to find the eigenvalues and the eigenvectors. So in this exercise, we have to find the eigenvalues and the eigenvectors for this matrix A. So here is the solution. In order to find the eigenvalues, here are the steps. So first of all, we have to compute the determinant of A minus lambda I. So we will compute the determinant of A minus lambda I and equate it to 0. So put the values. Determinant of this is A, this is lambda, and this is I. So if we multiply lambda inside, we get this value of the matrix. Now if we subtract these two matrices, we get this value. And if we take the determinant of this small matrix, it's very simple that you multiply these two values minus multiply 2 times 3, which is here. Now if you multiply these values with them and write this as 6, and after simplification you will get this quadratic equation. Now you can solve this quadratic equation by any of the method. So I am doing this by the factorization method. So it's very simple method. You have to multiply the coefficient of the lambda square and the constant. So the coefficient of the lambda square is 1. The constant is minus 4. So 1 times minus 4 is minus 4. Now you have to factorize negative 4 in such a way that you have to put two parts of negative 4 such that whenever you add them, you will get this thing. Whenever you multiply them, you will get this thing. So what are the parts of negative 4? So the first part is 2 times 2. Whenever you multiply, So 1 is negative, 1 is positive. It is negative 4. But if you add them, then you will not get negative 3. So these two factors are not okay. So if I do 4 times 1 and I write negative 4 here, negative 4 times 1 is negative 4, and negative 4 plus 1 is negative 3, so which is this. So these two factors are good. Here you will write lambda and here you will write lambda. So instead of negative 3 lambda, we will put this value and this value. So I will put lambda square as it is. I will put this 4 as it is. But instead of this value, I will put these two values, which were the factors of negative 4. Now, if you take common lambda from the first two terms, I will get lambda times lambda minus 4. And if you take one common from the second two terms, that means nothing is common. That means this thing will be as it is. Now you can check in the first term and in the second term lambda minus 4 is common. So I can take lambda minus 4 as a common factor, and here I will left with lambda and here I will left with 1. So lambda plus 1. Okay, since the product of these two things is 0, that means either the first term is 0 or the second term is 0. From the first term, if I take 4 to this side, it will be lambda is equal to 4. And from the second one, if I take 1 to this side, I will get lambda is equal to negative 1. Now, we will find the eigenvectors corresponding to these two eigenvalues. So, let's look for the eigenvalue lambda is equal to 4. So, for lambda is equal to 4, or for the any eigenvalue, in order to find the eigenvector, we will solve this equation. In order to solve this equation, we will put lambda is equal to 4 inside, and then we put the values, and I multiply lambda inside, and then if we subtract these two matrices, then we will get this and this value, and after simplification we will get this equation. So in order to solve this equation, we need to convert this coefficient matrix into the row reduced HLN form. So first we convert this matrix into row reduced HLN form. So suppose that this is the matrix, we are going to convert it into row reduced HLN form. So here we need 1. So in order to make it 1, you have to divide R1 by negative 3. And similarly, if you want to make here 1, you have to divide R2 by 2. So after division of first row by 3 and the second row by 2, first row by minus 3 and second row by 2, we get this matrix. And if I make here 0, how to make here 0? I can make here 0 as 1 minus 1. So simply I will subtract R1 from R2. So I will get this value. So this is the row reduced HLN form of the matrix. So if I put this value instead of A here, then what will happen? We will have this times this matrix times X is equal to 0. So if I multiply this matrix with this matrix, then we will end up with X minus Y is equal to 0. So from here if I take y to the other side, I will get x is equal to y. So the eigenvector can be written as x comma y, and in place of x I can put y, because x and y both are equal, so I can put y comma y. So if I take y common from both of the entries of this column vector, then inside I will get 1 comma 1. So this 1 comma 1 is the basis for the null space of A minus lambda I. So we will say that the eigenvector for this eigenvalue is 1 comma 1. So similarly we will find the other eigenvector for the other eigenvalue, since there were two eigenvalues. So for lambda is equal to minus 1, we have a minus lambda I times x is 0. So if I put lambda is equal to minus 1 inside, I will get a plus I is equal to 0. A plus I times x is 0. If I put the value of a and I times x is 0, if I add them, then I will get this. And after addition, after simple calculations, we will get this value. Now, in order to solve it, I will again convert this coefficient matrix into row reduced echelon form. In order to convert it into row reduced echelon form, here we will make 0 first. So we will use R2 minus R1 operation, because above is also 2. So after this operation, I will end up with this value. If I multiply this matrix with this, I will get 2x plus 3y is 0. Then if I take 3y to the right side, we will get 2x is equal to minus 3 by 2, 3y, and x is equal to minus 3 by 2 times y. Now, what is the eigenvector? That is x comma y. Put the value of y, which we have, put the value of x, we have already found. So if I put the value of x, then I can take minus y by 2 common factor. Since negative y by 2 is common, so here we have left with 3. Since negative is also common and here is no negative, so I have put negative. Y is common and divided by 2 is also common, but here we have no 2, so we have to multiply by 2. So the eigenvector is 3 comma minus 2. Hence the eigenvalues are 4 minus 1 and the eigenvectors are this and this.